In this video, we're going to practice L'Hopital's rule. L'Hopital's rule is a nice, handy trick that allows us to deal with limits of indeterminate value, but it only works after we've learned basic derivative rules. So you're not going to learn this at the very beginning of your calculus class. Usually it's somewhere in the middle of your first semester that you may be exposed to it. And it's something that as of 2017, the College Board is now going to include on their AP tests. It's a real handy trick that I enjoy a lot. If you want to follow along, the links to the companion worksheet are in the description below. So let's get started. So here we've got the limit as x approaches 0 of sine x over x. And when we plug in 0 in for this, we have sine of 0 over 0, and sine of 0 is equal to 0. And so this is one of the indeterminate forms right here, 0 over 0. So what L'Hopital's rule says to clean this up is to take the derivative of the top and the bottom. Now the thing to avoid is, remember, this is not quotient rule. Rather, we're looking at the top and the bottom independently. So we have limit as x approaches 0, and the derivative of the top sine is going to become cosine of x, and the derivative of the bottom is going to become 1. Now what L'Hopital's rule says is the limit for this is the same as the limit for this. Now we don't know what this is, but we might be able to work with this. So let's plug in 0 again. So plug in cosine of 0, and this stays as 1. Now cosine of 0 is 1. So the limit is equal to 1. And so L'Hopital's rule says that even though we don't know what 0 over 0 is, L'Hopital's rule helps to reveal that the answer is 1. So, looking down at number 2. Now, number 2 opens us up to a problem that some people have, and that is they think that L'Hopital's rule can work anytime when a problem is too difficult. And actually, no. Because if we plug in 1 here, we have 1 over 1 minus 1, which is 1 over 0. Now this is not indeterminate. Let me say that again. 0 over 0 is indeterminate. We're not sure what that is. But 1 over 0 is not indeterminate. So this limit does not exist. When it's over 0, we know that this graph has some kind of asymptote. And in particular, if you look at it as it approaches from both sides, it's not going to converge on the same spot. So this limit, no, this limit does not exist. Let's look down here. Here we have limit as x approaches 0 of ax over bx squared. If we plug in 0 here, we have a times 0 over b times 0 squared. But regardless, it's 0 over 0. So this is indeterminate. So we can use L'Hopital's rule. And we take the derivative of the top, we have a, and we have the limit of the bottom, which is 2bx. And so we plug in 0. Now a is just a constant. We don't know what it is, but it's some constant number that doesn't change. And we have 2b times 0, and so we have a over 0. Now this is almost the same as number 2, where we had a number over 0. So likewise, for this one, this is not indeterminate, and so the limit does not exist. So when we have indeterminate forms, the limit may not exist or it may exist. And L'Hopital's rule doesn't guarantee which way it's going to go. But this is why we do it, so that we can reveal it. So now, looking at number 4, here we're plugging in infinity. Well, infinity over infinity is another indeterminate form, and that's what we would get. We would end up having to plug in infinities on the top and infinities on the bottom. And subtracting 4 or subtracting 6 or multiplying by 2 or 4 doesn't change infinity. It's still an infinite number that's constantly growing. So L'Hopital's rule is needed here. So we want limit as x approaches infinity, and so we find the derivative of the top and the bottom separately. So the top becomes 4x plus 4, and the bottom becomes 2x. Now if we were to plug in infinity up here, we would still get infinity over infinity. And oftentimes with a L'Hopital's rule problem, you actually have to do it more than once, because just doing it once gave us an indeterminate. So we have to do it again. So the limit as x approaches infinity, so the derivative of the top over the bottom is 4 over 2. Now there's really no need for the limit because the expression doesn't have an x in it. So as x goes to infinity, this expression doesn't care. It's just 2. So here's a case where we had to go through L'Hopital's rule twice. So for the next one, here we're going to infinity, and here we have x cubed over 3. Now, infinity to the third power versus e to the infinite power, well, that's indeterminate for sure. So let's look at limit as x approaches infinity of 3x squared over e to the x. Now, if I plug in infinity here, it's still going to be indeterminate, so we have to go again. Limit as x approaches infinity of 6x over ex to the x. Again, still going to be infinity over infinity. So the limit as x approaches infinity of 6 over e to the x. Now here we have 6 over infinity. Now what that is basically equivalent to is 0, because what you have is you have 6 over a number that is getting constantly bigger. And so if our denominator is constantly growing, this whole expression is getting closer and closer to 0. Now number 6 at a glance looks almost identical to the one above it, but actually it's to the negative infinity. So if we plug in infinity to the third and e to the negative infinity, now you can cube infinity, that's still infinity. But e to the negative infinity, at first glance, some people would say, well, that's just negative infinity. Actually, it's not. And I apologize, that should be a negative up there. So we should have negative infinity on top. But if you think about the graph of e to the x, if I just draw a quick sketch here, here's the graph of e to the x. The idea of it going to negative infinity means it goes off the left-hand side. But the graph of e to the x gets closer and closer to 0. So that means we have negative infinity over 0, like that. So by dividing by 0 here, we have a limit that does not exist. So now, moving on to the next one. Now here you might see this, you might recognize that you probably saw this when we were looking at algebraic derivatives. But now, because of L'Hopital's rule, we're able to tackle something like this without it. Now we can just use L'Hopital's rule and find the derivative separately. Now let's check. If I were to plug in 0, we'd have square root of 4 minus 2 over 0. Square root of 4 is 2 minus 2 over 0. So we have 0 over 0. So that is indeed indeterminate. So we do need L'Hopital's rule. So on the top, the minus 2 goes away. And so the square root of 4 minus x squared, I'll just rewrite that up here as 4 minus x squared quantity to the 1/2 power. So the derivative is 1/2 times 4 minus x squared to the negative 1/2, but because it's chain rule, we have to multiply by the derivative of the inside. And the derivative of the inside is negative 2x. And the bottom is 1. Now before I take the limit, let's simplify this expression a little bit. Let's clean it up. And so the 1/2 and the negative 2x stay on top, just become negative x. And on the bottom we have square root of 4 minus x squared. Now if we plug in 0, we have negative 0, but still 0, over square root of 4 minus 0 squared. So we have negative 0 over square root of 4. And it doesn't matter that we just have a number on the bottom that isn't 0. So we have a limit of 0 here for this one. All right, moving on to number 8. Here we have a similar one to number 1. We have sine. We're plugging in 0. And so we know that sine of 0 is 0, as well as sine of 0 on the bottom as well. So that's indeterminate. So L'Hopital's rule says we take the derivative, and both of these are going to involve chain rule because we have something other than x on the inside. So the derivative of the outside is cosine of ax times the derivative of the inside, which is a. Same thing for the bottom, except that there's a b instead of an a. And so when we plug in 0, we have cosine of 0 times a over cosine of 0 times b. And cosine of zeros are both worth equal to 1. So our limit here is a over b, those constants. Down with number 9, here we have ln over x squared minus 1. So if we plug in 1, ln of 1 over 1 squared minus 1. So on the top we have 0, and on the bottom we also have 0. Another candidate for L'Hopital's rule. So we take the derivative of the top, ln of x becomes 1 over x. Again, that's just the numerator. Let's not forget our limit as x approaches 1. And on the bottom we have 2x. Now let's simplify that algebraically. So instead of dividing by 2x, we'll multiply by 1 over 2x. So we have limit as x approaches 1 of 1 over 2x squared. So now if we plug in 1, we get 1 over 2 times 1, which is 1/2. So there is our limit. So on the last page, here we have limit as it approaches infinity. But here notice that it has negative x. So if I were to write this, we'd have e to the negative infinity over 1 plus e to the negative infinity. But I said before, e to the negative infinity is essentially 0. So this is actually a fake out because we have 0 over 1. So actually the limit equals 0 here. So this is a problem that doesn't require L'Hopital's rule. And that's another important lesson to learn about L'Hopital's rule, is not just how to do it, but also when it's not needed. So for the last one, here it's going to infinity. And so if I were to plug this in, we'd have infinity on the top, square root of infinity squared plus 1, which would work out to just infinity anyway. So L'Hopital's rule says x goes to infinity. On the top we have 1. On the bottom, this is x squared plus 1 to the 1/2. So the derivative is going to involve chain rule. So we have 1/2, bring that down, x squared plus 1 to the negative 1/2 times 2x. Now the 1/2 and the 2x can stay down, but because this expression has a negative, we're going to put that up top. So here we have limit as x approaches infinity, square root of x squared plus 1 all over 1/2 times 2x is just x. So having done L'Hopital's rule, we ended up with the reciprocal of the expression we started with. And if we plug in infinity, well, it's just going to be the same thing but flipped upside down, infinity over infinity. So this isn't enough right here. We need to use L'Hopital's rule again. Now here, the bottom is going to have a value of 1. The top, we're going to have 1/2 x squared plus 1 to the negative 1/2 times 2x. Because again, it's essentially the same expression as what we had up here. But now, this expression with the negative exponent is now going to go down. And if we write that, the 1/2 times the 2x that stays up top is going to be x over, and we have square root of x squared plus 1. Now at this point, we've done L'Hopital's rule twice, and notice where we ended with versus where we started. It's exactly the same. So actually, if we were to keep doing this, we'd be going back and forth between these two forms forever. And so for this problem in particular, L'Hopital's rule doesn't help. It keeps us in this infinite loop. So actually, L'Hopital's rule is of no help in helping us to find this limit. Thanks so much for watching. If you liked the video, give it a thumbs up. If you want to see more videos like this, please click the subscribe button. If you're a student, share it with your classmates. Or if you're a teacher and you like this, share it with your colleagues or share it with your students. If you want to help support the channel, click the Patreon link. Thanks so much for watching. And remember, the best way to learn something is to do it.